Okay, welcome everyone to this Friday morning session. Our first talk is by Taushif Ahmed from University of Regensburg, and he's going to tell us about massive two-loop QED form factor.
Thanks a lot, Lorenzo, and thanks to the organizers for the opportunity to present my work with Giulio, who is a PhD student at Padova, Federico, a postdoc at Mainz, Syed Mehdi Hassan, he is also a postdoc in Regensburg, and Pier Paolo from Padova. So today I'll be actually talking about this QED form factors at two-loop level. So basically here actually two mass scales are actually involved. One is this external massive particle, but there is another mass that is involved which is running in the loop. Okay, so this analytic evaluation of this QED form factor, this is actually quite an old topic because it actually goes back several decades ago, which started like around 70s when people actually started computing this QED form factor. But then actually later it started picking up when people started computing the similar form factor in QCD. So this project, that electronic form factor, that when these electrons have actually non-zero mass, this is considered to be one of the actually pioneering projects because it really triggered a huge amount of development in the calculation of this multi-loop form factor, as well as like other form factor when you have many different legs as well. And this is among the first calculation where people actually realized that the simple set of classical polylogarithm is actually not a complete basis which can really explain all the different multi-loop results that you want to actually compute. So you need something that is beyond classical polylogarithm. And later this started with this harmonic polylogarithm, and now like Goncharov polylogarithm, elliptic polylogarithm, and even beyond. So this calculation that actually triggered many other calculations in QCD. And in particular, if you look at this heavy quark form factor in QCD, so at two-loop level, when people started computing this heavy quark form factor, initially, they computed when there was no mass scale that is present inside the loop. Okay, only these external legs are actually massive. But eventually, people started also computing this kind of form factor where you have again another mass loop that is involved within the loop. But the important point is that these two mass scale, which is the external massive and the internal mass, these two are actually exactly same. And there is also another kind of contribution when you have gamma 5 actually involved, like some axial quantity. And as you know that if you have an axial quantity, if you have odd number of gamma 5 in a closed fermionic loop, that actually gives rise to something called axial anomaly. So that is something that people had to take into account. And in this paper, basically they have computed this anomalous contribution that gives rise to this two-loop form factor in QCD. And also, not only by explicit computation, but also by exploiting the RG properties of this form factor, because one can show that if you look at the massless form factor, this massless form factor actually gets exponentiated. But massive form factor, entire massive form factor, that although does not get exponentiated, but if you look at only in the high energy limit, you can show that form factor also actually obeys similar kind of behavior like exponentiation. And one can show that this form factor actually obeys some differential equation, which is often actually called some integral differential equation called K and G equation. And by exploiting the properties of this differential equation, one can really predict some of the terms in the next loop order. And in this paper, so this kind of thing actually started by Soed Mock and Mitov when they basically looked at this kind of behavior for massive form factor. And in this paper, basically, we exploited this kind of property, and we also actually predicted some term at the three-loop level. Now, also, if you look at that, this kind of like topologically, if you think from the perspective of multi-loop computation, and if you look at this Higgs boson decays to some quark, let's say some non-zero mass of this bottom quark, and some top loop actually involved. This kind of computation is actually all along the same direction, or along the same direction from the perspective of multi-loop computation that people actually did. And as you heard from Andreas, that in massless form factor, there was a remarkable progress and some groundbreaking result at this full loop level. this is excellent result, and so people have even predicted some of the results at 5 loop level by again exploiting this RG behavior of the form factor. And very recently, people have actually computed in this large NC approximation this heavy to light form factor, like if top actually decays to some W boson and bottom, then what will be the form factor in the large NC approximation that people have actually computed quite recently as well. So you see that there is a huge development in the computation of this form factor, but still there is something that is actually missing from this 2-loop form factor when if you have actually 2 different mass scale. Let's say you actually consider the electron form factor, but inside there is actually muonic loop. If you consider the bottom form factor with non-zero mass of this bottom, but inside there is actually top loop. So this kind of thing is still actually missing. And in this work, what we have actually tried to address, we have tried to compute this, this form factor, which is essentially the last missing ingredient of this complete 2-loop form factor, okay? Where we have basically external electrons, which are massive particle, and there is also internal massive particle. You can actually think of this as a muon, and this ME is actually not equal to MI. And this is the form factor that we have basically computed in this work. So our goal of today's talk would be to look at sorry, actually this will be QED correction. So 2-loop QED correction in analytic form. And then we will see that this result can be actually expressed in terms of Goncharov polylogarithm. And one can also express this Goncharov polylogarithm in terms of some classical polylog as well, which is sometimes actually efficient for numerical evaluation, or if you want to do some series expansion of the form factor. Although nowadays, actually, if you can equally do this numerical evaluation of Goncharov polylogarithm using GNAC, both are actually equally good. And we have also tried to check our result by reproduce the mass-dependent contribution of this leptonic anomalous magnetic moment. So these are the goals of today's talk. Now, if you want to calculate the form factor, so the first thing what one can actually do, one can look at what is the Lorentz covariant structure of a form factor of this particular amplitude, and you can actually break down what are the independent structure that you can actually have. So if you look at that, since we have actually considered not only vector, but also axial vector, then we have scalar as well as pseudo-scalar. So for the vector part, people can show, it can be actually shown quite easily that there are only 2 form factors which actually survive. One is F1 and F2, which are sometimes actually called Pauli and Dirac. Okay. And if you introduce this pseudo vector, which is basically gamma mu gamma phi, then again, this will also actually have a similar decomposition in terms of this independent Lorentz structure, and that is G1 and G2. And you see that this is basically gamma mu gamma phi, and there is gamma mu gamma phi and Q mu. Right? Q is the momenta of this vertex. Then you have similarly you have scalar and pseudo-scalar, which basically exhibit very simple structure from the Lorentz covariance point of view. Now, if you look at the pure photonic vertex, because QED is actually parity invariant, therefore actually there cannot be any gamma phi that survive. Therefore, if you look at only the pure photonic vertex in QED, then this term will actually not survive, and that one can actually check it explicitly by doing the calculation that we will see actually in the next slide probably. Or one can even actually do this calculation, simple algebra, and one can show that this term will actually not survive, which is expected because of this parity invariance of QED. And while doing this Lorentz covariance decomposition, in principle, one can have another term, which is F3, that is actually proportional to the momenta. But due to the word identity, QED word identity, that term will actually not survive. So therefore, only there are 2 form factors which we really have to calculate. And once you make the Lorentz decomposition, then you can actually construct the projectors. Essentially, what you will do that you have this all the independent Lorentz structure, you calculate the gram matrix, and then you actually construct the projector. And this projector one can actually construct in D dimension, or one can actually construct in 4 dimension, because there are certain issues that whether people should compute the projector exactly in D dimension by looking at all the structures which are independent in D dimension, or whether people can look at only in the 4 dimension and then it will be sufficient. But when you have actually gamma phi, then as I mentioned in the beginning, that there are certain issues. We know in principle that how to handle gamma 5, but still at many different scenarios, we encounter certain surprising phenomena involving gamma 5. Since for this particular process, for this particular vertex correction, there is no triangle, like odd number of gamma 5 roaming inside the loop. Therefore, there is no actually anomaly. Therefore, it's perfectly fine if you employ this anti-commuting gamma 5 to compute this form factor. And in fact, we have employed this anti-commuting gamma 5. However, if you want to calculate the same quantity using this non-anti-commuting gamma 5, that you also actually you can do it, but the additional thing that you have to do, you have to basically introduce additional counter term because of this non-anti-commuting gamma 5, right? And let me make actually few comment that, as you know, that the dimensional regularization that actually preserve Lorentz and gauge invariance, but it breaks the chiral invariance. And the reason is basically gamma 5 is inherently defined in 4 dimensions. And people often follow this prescription by T. Hoopt and Veltman and Bryton, Lohner, and Meissen, where you define gamma 5 in terms of Levi-Civita symbol and 4 gamma matrices. But the problem is that as soon as you define in this, it actually breaks the defining properties of gamma 5, namely this anti-commuting property of this gamma 5. So in principle, what we do that whenever we have a gamma 5, you can actually decompose your amplitude by exactly the same way as you do for the vector part. You just multiply 1 gamma 5. But the problem is that this kind of decomposition, that is actually linear complete in 4 dimensions, but in general, that is not linear complete in D dimension. That one can actually easily show it. And therefore, when you have this, you want to use this non-anti-commuting gamma 5, which is essentially if you have some anomaly present in your calculation, then it is actually not easy to construct this full D-dimensional linearly complete basis that will be valid to all loop order. And even with an incomplete basis, if you really keep this full dependence, then you will see that sometimes the size of the projector will become so large that it's really inconvenient. And initially, at least few years back, it was not entirely sure that whether we can set D equal to 4 to simplify the calculation to construct the projector. But later, nowadays, actually people do it because people have seen evidences that this will actually give you the correct result as long as you are interested in looking at only the finite remainder at certain loop order. And therefore, when you have some axial quantity, what you can do, you can look at what are the independent structure in 4 dimensions. You set D equal to 4. You calculate this entire scattering amplitude, whatever you want to calculate. And then you actually look at only the finite remainder. And this is an observational fact that where in this paper, basically here actually we have seen in explicit example, and also Tiziano and Lorenzo, they have also actually discussed in this paper that if you derive this projector in 4 dimensions, that can be really used in D-dimensional calculation, and still that will lead to correct physical result of finite remainder, where we are mostly actually interested in. So this is just a side comment if we want to calculate this quantity using non-anti-commuting gamma 5. And for this case, as I told you, that the axial part actually decouples from the vector part. So for example, you can define 4 quantity. By combining this 4 quantity, you can actually calculate. You can basically calculate this form factor F1, F2, which is the vectoric form factor, and this axial vector form factor G1 and G2. And just by doing some algebra, one can show that this F1 and F2 can be expressed solely in terms of P1 and P2, which are actually the component of the projector. And G1 and G2 can be expressed in terms of P3 and P4. And these 4 component, out of these 4 component, we actually constructed all the projectors. So therefore, it's quite clear that F1, that the vectoric form factor and the axial vector form factor, they basically decouple from each other. Now one can actually explicitly verify it. For example, here, you will see that if you have only a single gamma 5, then you can replace the single gamma 5 in terms of this Levi-Civita and the 4 gamma matrices. But once you perform this loop calculation, then essentially you will have, because it's a 3-leg process, there are only 2 independent momenta. So with this epsilon, always there will be some quantity which will be symmetric in two of this argument, Lorentz argument, and therefore this entire quantity will actually vanish. So one can explicitly verify that, okay, this is perfectly fine. Now for this form factor computation, so we have followed basically usual method. We generate the Feynman diagrams, you apply the projector, you do all the spinor and Lorentz algebra in D dimension, then you apply this IVP. For this IVP, we have basically used light rate and fire, and then you calculate all the master integrals using the method of differential equation, and you can actually express in terms of Goncharov polylogarithm. So let me briefly mention that how we compute these integrals. So for this case, there are only 7 master integrals actually present, and we convert it into a canonical form utilizing the method of this Magnus and Dyson exponential matrix. And we encounter basically 3 square roots that we managed to rationalize with the help of rationalized roots, where we have basically moved from our original set of variables to x and y. And what we have actually seen that if you define if you actually transform this variable using these 2 relation, then the 7 canonical form of this integral is basically take in this particular form. Okay, where this epsilon is basically factored out, and this matrix dA that can be written in terms of D-log form, where this eta basically there are 9 eta that we have actually encountered, so that means these 9 structures that actually appear, and this M is basically just rational numbers, matrix of rational numbers. So we have actually solved this problem in unphysical region where S is actually negative. So that means all the eta 1 to eta 9, they are basically real and positive in this particular region.
Taushif, yes. I'm sorry, I don't understand. So T1 and T2, the external momentum is not flowing, and are they actually bubbles?
Yes.
Ah, yeah. You really have. Okay. Yeah. So those are like very simple. I mean,
yes, simple. There you can actually evaluate those explicitly, just integrating. Okay. Okay. But one can actually analytically continue it to physical region by putting S goes to S plus I epsilon, and in a paper by Thomas German and their collaborators, they have basically explained how one can actually do this analytic continuation. So to fix the boundary condition, it was also not very difficult to fix the boundary condition, because, for example, the first 2 integrals, they are basically, you can explicitly integrate those and you can fix the boundary condition. For the remaining set of integrals, what we essentially did, we actually did S goes to 0 limit, and with mi equal to me, because if you have 2 mass equal, then those integrals are essentially actually known. And by comparing these 2 things, you can really fix what is the boundary values that you need. And we have also actually cross-checked this boundary values using this AM flow at S equal to 0 and mi equal to me, and reconstructed the result using PSLQ algorithm. So we have expressed the result of these integrals in terms of Goncharov polylogarithm up to weight 4. And these master integrals are also actually numerically checked against this numerical program by SecDec as well as AM flow. And also in this paper, they actually computed this integral because they needed it, and we got a perfect agreement by comparing with this paper. Now, once you actually compute the master integral, then you can take those result of this master integral and get the bare form factor, but then we have to renormalize. And one can actually renormalize it in many different ways. So what we have actually followed that the diagrammatic way of renormalizing in on-cell scheme, because if you look at this, is a very simple vertex kind of diagram. So we can really actually identify that what are the different counter terms diagrammatically that we can introduce such that the divergence basically cancel. And for this particular vertex diagram, we have to actually introduce 2 different counter terms. This counter term, which is basically subtraction of the 1 loop sub divergence that you will get from this vacuum polarization. Okay. And for this particular subtraction, you can calculate this Z3, the renormalization constant that you need in this on-cell scheme, and that is essentially, that is essentially you can actually calculate by demanding this particular equation. Okay. And the second kind of subtraction that you need, that actually cancels the genuine two-loop residual divergence of this vortex that you will get, okay, because this is basically at the level of at the second order, not at the first order. And this renormalization constant again actually defined similar to the previous case, where basically if you add these two diagram and take the s goes to 0 limit, and then also actually you can derive what is the value of this Zj. That is the renormalization constant for this residual that will basically cancel this two-loop residual divergence to the vortex. So let me just briefly explain that how we actually did it diagrammatically. So if you look at, for example, this particular one, which is the simpler one at the because this is at the one loop level. So you look at this particular Feynman diagram, you apply the IBP, then you can show that this diagram can be written in terms of these two integrals. And you see that there is basically 1 over L square is actually present in the coefficient of these two integrals. Now to take L square goes to 0 limit, because that is what we need, what one can actually do, we can do the power series expansion of this particular integral. Because if you look at this integral, there will be, let's say there is a momenta L that is actually entering, and one of the loop momenta is K. Then the another one will be, let's say, K plus L. Now you can actually do this power series expansion with respect to small l. Then you will get this particular thing, because the first one will be 1 over K square to the power 2. And therefore, that is basically the simple bubble with a dot. So you can actually do this kind of expansion. And once you do that, then you can compare that the first term, this first term is basically essentially this one, and the second term is basically the first order derivative of this original integral. And by playing with this kind of thing, by comparing all these different quantities, you can essentially actually get what is this renormalization constant Z31 by demanding this particular equation. So this is how basically we perform all the expansion that we actually needed for this kind of computation. And similarly, in order to calculate the ZV2, which is the renormalization constant at second order, that cancels the residual divergence at the two-loop level, then also actually you can demand that this kind of equality, and that means what you have to do, again, you have to actually expand this kind of diagram around s equal to 0. Okay, and we have actually followed the similar technique. In fact, we did it in 2 different ways to check whether we are actually getting everything correctly. And by doing exactly the same machinery, by expanding and comparing these two things, one can really fix what is the ZV2 that we need in order to cancel the divergences in this on-cell scheme. Okay, so after renormalizing, what we have actually seen that these are the simple renormalization constant that one can actually find out. So diagrammatically, this one loop renormalization constant can be represented in terms of simple bubble times some coefficient. The renormalization constant J2, where basically J actually runs from vector and pseudo vector and scalar and pseudo scalar, that can be actually expanded in terms of these 4 different integral. And once you put the values of this integral, then you will be able to determine what is the renormalization constant that we need in order to get rid of all the divergences. Now, for this case, we have actually used this anti-commuting gamma 5. Therefore, we really don't need to introduce any additional counter term that one, in principle, should need if one wants to calculate using the non-anti-commuting gamma 5. And just a little bit digression that sometimes, for example, in this particular process, where if you want to calculate this production of the Higgs boson in association with G boson through quark annihilation in an effective theory, what we actually found out that if you simply introduce the counter term that is given by Larin at two-loop level, that is actually not sufficient. Okay, you will not be able to get rid of all the divergences that you will get from this particular process. So what one has to do, one has to actually introduce an additional counter term. And that we found out that, in fact, what we had to do, that is one of the ways that we found out that one has to construct an effective vortex involving these 4 different particles. So the message is that if you want to calculate using non-anti-commuting gamma 5, sometimes you encounter very surprising thing that we a priori we actually don't expect probably. So what actually Andreas mentioned that although we know that how to handle gamma 5 in multi-loop computation, but in order to address all the issues once and for all, probably we need to do more and more work And that is, I totally agree with that one. So this renormalized form factors we have expressed in terms of 74 Goncharov polylogarithm up to weight 3. And the form factors are, as expected, very small, just few kV. Some of the GPL, they depend on X with the weights of simple looking this kind of form, and the remaining GPL that depend on Y with the weights like -1 and some 1 and iota. All the form factors we basically independently computed with a different choice of variable as well. Yes, thank you. And the master integral that were actually present in this paper as well, and we found a perfect agreement. So after that, once we managed to get the result in terms of Goncharov polylogarithm, we also actually converted the result in terms of classical polylogarithm. And here, what we actually did, that we used the code that is given by Yalte and his collaborators, but we did little more extra thing, because if you directly use this code, what you will see that the final classical polylogarithm that you will get, that still has some theta function as well as signum function. But what we did, we exploit the properties of this GPL through Shuffle algebra. Because if you, let's say, actually look at what are the GPL that is appearing in your form factor, you apply the Shuffle algebra, then what you will get the same different set of many different GPL. And for each GPL, you apply this actually code, okay? And sometimes we also have to add I delta parameter appropriately. And then you actually check that whether the final result, what you will get from this code, without this signum as well as the theta function, whether numerically these two things are actually matching. And for each case, what we have found out that for one particular set of GPLs that you get from the Shuffle algebra, you really don't need to introduce any Heaviside theta or signum function. You will get a perfectly valid polylogarithm without this function. So that is a bit of convenience that we actually found out. So we don't know whether this is generically actually true, but this is some based on some observation that we have basically found out that one can convert GPL to polylog in this nice looking manner. And the last thing that the form factor F2, which is basically called the magnetic form factor, if you take the S goes to 0 limit, that actually gives you to this anomalous magnetic moment. And what we checked, that if you take this S goes to 0 limit, then it reproduces the result that is already actually known in the literature. So this is an indirect way of checking what we actually calculated it. And the equal mass contribution, if you put this two mass equal, Z equal to 1, then you will see very, very small, very simple looking number. So that brings me to my conclusion that a calculation that basically started many decades back. Probably this is not a very complicated computation, but this is a last missing piece. Now, basically, we can say that our complete two-loop electron form factor with a muon correction is actually now completely over. And the result of this form factor actually can be used in many different scenarios. For example, one can calculate if one is interested in calculating the decay rate of a neutral Higgs boson or the pseudo Higgs boson to some set of quark pair HQQ bar X, then also actually one can do the similar calculation what we did it here. Massive form factor in QCD with two different mass scale, that also actually this missing part one can actually now calculate it. And this is also an important thing for muon electron scattering, because if you look at muon scattering and if you rotate it, then this is exactly this contribution actually will get it. And as outlook, as I told you that for massive form factors, if one looks at in the high energy region, then one can find out that this form factor actually satisfies some nice looking differential equation that is called this KG equation. And by utilizing the behavior of this RG equation, one can really predict certain terms in the next loop order. So this is something that we are actually currently working on it, because if you have this kind of contribution where you have internal massive loop, they obey the similar kind of KG equation, but not exactly if there is no mass scale present inside the loop. So Swain Mock and his collaborator, they they did actually discuss something related to that, but still we need to work on it in order to get this thing actually done. And things will also actually become interesting at 3-loop level, because if you go to 3-loop level, then and particularly for the pseudo vector part, that will also actually give rise to certain interesting thing that we think. So okay, so thank you very much for your attention.
There's 3 loops, you could have 3 masses.
Not really. We don't want 3 mass. We want only 2 mass.
Okay, questions or comments or for Taushif? Looks like everybody is. Julia?
Yep.
Oh, thanks for the nice talk. When you compute the counter terms for the form factor, so, one thing that I had in mind is not there any IR divergence that
No.
Okay,
No.
Because I don't expect collinear, but soft.
No, it's not there. Basically,
Okay.
reduce this mass. Yeah.
Yeah, but you still have a gluon that goes through, so that.
Actually, here you won't get any IR divergence, right?
Okay, that's great.
Yeah.
Thanks.
Further questions? Actually, could you say again about this anti-commuting gamma 5?
Yes.
So in general, you can't do it. Why is it that here you can?
Here actually, because we don't have any anomaly present here, because we don't have this famous triangle diagram.
Okay.
Like if you have odd number of gamma 5 present in a closed harmonic loop,
okay,
then you have to use this on a non-anti-commuting gamma 5.
Okay.
Otherwise,
Okay.
there is a problem.
You had said it. So very good. Very well. So if we don't have any further questions, let's thank Taushif again.